morning, ladies and gentlemen. John Belkowitz, Intelligent Concrete, where we make concrete do the impossible. Wanted to do a morning coffee talk this morning on abrasion resistance. We've had a few coffee talks on abrasion resistance using scanning electron microscopy and kind of debunking scanning electron microscopy and showing where it can be used. What I wanted to do is continue with abrasion resistance and do a 5-minute spiel on what abrasion resistance is, and what are some of the best ways and some recommendations for increasing abrasive wear resistance with different additives, admixtures, and possibly supplementary cementitious materials or alternative binders. So what abrasion resistance is, if you think about it, when we've got this, I call this the, our top surface here, our gray stuff that you constantly see on the sidewalk and the pavements. I call that sacrificial layer. And what basically happens with abrasive wear is whatever type of traffic you have, or erosion, so it's either vehicular traffic, steel wheel tire traffic, foot traffic, or for dams, locks, levees, spillways, those types of things. It's water and soil, water and aggregate, water and tree branches, water in, some type of underwater abrasion. And you've got this stuff rolling over the top surface of your hydrated cement matrix, if you will. And what it's going to do is it's just going to start knocking down the asperities, or these microscopic mountains that make up, the developed phases of that hydrated cement matrix. And as it starts doing it, if you can imagine, it rolls and it breaks it off. It's going to start breaking down into the surface, and depending on how nasty the abrasive wear is, if the material's tougher than the concrete, even rubber over time, with enough, wear or just rolling over it, is going to have, an impact on the concrete surface. So, as those things, let's say steel tires or steel wheels from forklifts, as they roll over, what they're going to start doing is basically tearing off that hydrated cement matrix until we go from that surface, that sacrificial layer. And that layer is fairly soft. It's that hydrated cement matrix, the softer matrix that embeds a stiff and elongated fiber, which is our aggregate. So I call that the sacrificial layer because, you have to lose something to abrasion. But as it goes through that, we start losing that cement paste only surface, and we get into a combination between cement and some smaller or finer aggregate particles from your sand or even from your coarse aggregate. And despite the fact that we're losing cement, or in a cross-sectional area where we're using more aggregate than cement, what you're going to find is you're also getting a harder and tougher material as you go deeper into from the surface to the subsurface and then into the body of your concrete. And the reason why I say that, the top surface, better said, is that first line of defense. And it's a very poetic way of saying it. And the reason why I say it's that first line of defense, that it is going to be that sacrificial layer, but you lose that cap, if you will, and that cap is going to have underneath it a denser surface. And more often than not, that top surface, unless it's treated right, or you're going to have a little bit more porosity to it. You might have some micro cracks. It might be subpar compared to the subsurface with the aggregate. And as you go deeper, anywhere between an 1/8 inch to 1/4 of an inch, depending on who finished it, you're going to start seeing these coarser aggregate in here. And the way it works is with abrasive wear, especially if you're looking at some of these tests, you see this initial depth of wear. It's a very steep gradient, a very, how would you say it, a positively increasing curve. And that's that sacrificial layer of that cement paste. And as you start going into that subsurface, you start hitting some of that aggregate, you see a plateau of that abrasive wear, that depth of penetration into, you know, your surface. And that could be if you're doing a test within minutes, and if you're looking at a concrete roadway or local or state artery, it could be years or even decades if it's some awesome type of concrete. But you start biting into that surface, and now instead of it being just the cement paste that you're having or that abrasive wear is having an impact on, it's a combination between the aggregate and the cement paste. In the last two videos that we were looking at with the scanning electron microscopes, they were looking at the hydrated cement matrix at the microscopic scale and identifying the difference between a subpar concrete and a ultra high performance concrete as it germane to abrasive wear, and what the two different hydrated cement matrices look like. But here it's about not only just the cement paste and the aggregate, but also the interface between the two. And what we want to see is, one, a hard aggregate, but two, a hard aggregate that is anchored into our cement paste. And unfortunately, most of those hard aggregates, some of them I should say, are normally can have be a dirty product, so that they have a lot of fines on the surface, and there's actually a bad interface between the hydrated cement matrix and that aggregate. So instead of having aggregate that are locked in like you see here, the aggregate are almost polished at the surface, and that's what we want. You're going to have aggregate that's going to be torn out, especially your smaller aggregate, your sands, your 3/8 rather than your larger stuff, unless you're looking at some underwater abrasion. And I tell you, with this sample, I don't know if we could see it if I shove the sample in the camera again on the iPhone, but you can actually see some pop outs or tear outs of the aggregate on the surface. I don't know if you can see that. We'll take some pictures out later. Okay, so El Khalil, asked the question, how can we stop hydration reaction due to the scanning electron microscope test? And, his question is based on the idea that the scanning electron microscope, when you place a sample in there, normally we place these little chips, and I don't know, maybe I should really have a stage over here with some samples on it. But even if it's a small sample, you're normally going to have some water vapor pressure in there. And good morning, by the way, good morning, gentlemen. I'll do the wave thing over here. So normally you're going to have some vapor pressure because of hydration. So there's a couple of things that you want to do before you get your sample in there. The first thing is, like El Khalil said, is stop hydration. At a certain point, you want to, take a snapshot in time of that hydration. Yeah, I don't have any samples, El Khalil. Sorry about that. But you want to stop that hydration to take that snapshot in time. There's a few ways of doing it. One, you could put it in, I believe, an ethanol alcohol or some type of alcohol to basically dehydrate it and yank all the water out. Two, you could throw it in the oven. This is a little bit tricky because you are going to be causing some micro cracks if you drive up that temperature a little bit too much. And then three, a method that we're going to start trying out here soon is putting the samples in a cryo cell. So this is commonly done with the ASTMC 666 test. If for some reason, you have a chamber and your chamber is full and you can't start samples, you can put your samples in the freezer and keep them at a frozen state until you can put them in that freeze-thaw test. And with the cryo cell, especially if you're looking for certain phases of development that would be destroyed if you dried out the cell, freezing them and then using a forced ion beam to cut the sample and take snapshots of it to get a three-dimensional analysis is another way of looking at it. But you need a pretty high magnification and a very sensitive and a very special microscope. It stops. The question was, how does the alcohol stop the hydration reaction chemically? So the cement hydration reaction, man, El Khalil, you're asking some tough questions. So the alcohol stops the reaction because it, cement hydration is a hydraulic reaction. It's based on the combination of water and cement to dissolve the dicalcium silicates to create that calcium and silica gel in a pore water solution to develop those phases. Hi, Di. Those phases for those phases for the hydrated cement matrix. I'm sorry. Auntie Di just got on the phone, so I got a little bit nervous. But yeah, so that alcohol reaction is basically going to yank that water out. So you're not going to have that water for reaction. And obviously, you're going to want your samples to be small. So assuming you use one of those 3 methods to stop the reaction from there, the other thing is you want to make sure that your sample is as dried out as possible, and that's the trickiest part. It's either you can do it in a vacuum or an oven. If you do it in an oven, you run the risk of causing cracks. And then you don't necessarily need to do it if you are, using an environmental microscope that can take some of those higher vapor pressures. So the next thing that you can do is you can sputter coat it. You can sputter coat it with gold or with carbon to make that surface a little bit more conductive, because the thing is, most of the hydrated phases or the sample itself is non-conductive compared to other material. No. Keep asking questions, El Khalil. I love questions. But anyway, getting back to the abrasion resistance. So, to increase the abrasive wear of concrete, there are certain things that you can do. Reducing the water cementitious ratio to make a denser, more refined, hardened sponge of concrete is one way of doing it. Using supplementary cementitious materials like, the best dry one out there is microsilica or silica fume. There's also Classa, fly ash, slag, metakaolin. Colloidal silica is one of my favorites. And what you're basically trying to do is refine that hardened sponge of concrete to make it denser so it doesn't tear away the surface. You want to make it harder to resist those abrasive forces, but not only that, lock in that aggregate. And as aggregates go, you want to use something that's a very hard aggregate, but also a clean aggregate too, and that might be difficult to come by. And then you can also use these really cool admixtures. I already talked about colloidal silica, but carbon nanotubes are the bee's knees when it comes to abrasive wear resistance. So, there's a lot of technologies. There's a lot of paper out there that talks about using new and emerging technologies to increase abrasive wear, even fibers. I mean, there's some awesome papers published out there by Inforce on how to use fibers for abrasive wear resistance. We've helped work with them on those. So there's a lot of great information. Adam, what do you got? I'm planning to use siloxane sealer around the house exterior, and we use it in brick and concrete. The sealer is apparently breathable, but I just wanted to get your opinion if it's a good idea. Yeah, I mean, I don't know where you live, Adam, but most sealers are great, especially when we're looking to increasing the resistance to de-icing salt attack. There's a company that we work with that makes a topical additive and an admixture for a topical additive and admixture for increasing resistance to de-icing salt and de-icing brine attack. So that's really where we're going with that type of stuff. Also, so the question was, so how does a breathable, so you're basically putting it on there. There's 2 ways of going with these breathable technologies. Either there's some technologies that have either silicas or silicates in there that they claim seal the surface, but again, it's not like an epoxy coating that totally covers the surface. And that's what you're getting from these, where they seal up the pores, but you're not putting enough of the product on there to create an impermeable layer. So it's almost like you're putting a bunch of layers of a ping pong ball net on there. I don't know if that's the best analogy. But as you put more and more and more layers on of these sealers, eventually either the sealer is going to build up on itself and create a less breathable, a less permeable, and a more impermeable layer. If you think about it, an epoxy coating compared to some of these sealers is almost totally impermeable. I would say it is totally impermeable, especially if you put an epoxy coating on extremely thick as compared to some of these that you're putting on 100 square feet per gallon. They're drawing into the surface, so you're not truly covering or sealing the entire surface, so you still have avenues for some of the vapors to leave the concrete, but you are sealing up the pores, so it's harder for that negative pressure to get through into the concrete. Bear in mind, though, you know, especially these siloxane, silane sealers, they're great. I mean, they're freaking awesome sauce. But you've got, I mean, when people walk on them, when people use your sidewalks, your concrete, your brick, you are going to tear open that surface. So, I mean, either every season, every other season, or every 3 seasons, you'll need to replace it. Either rip and strip the entire thing and put some new stuff on, or you know, place it on top of it. No problem, man. Okay, so I got time for one more question, then we got to go make up a bunch of concrete. Can you make a later Q&A session about the use of fiber in concrete? Yes, absolutely, El Khalil. My plan for that is we've been working with a wonderful company in New Zealand on their fiber technology. And I want to do a few interviews for them on fibers in concrete as they see New Zealand start to pick up a technology that has been matured in the United States. Then it just happens to be that this company has some amazing and awesome new tech for fibers in concrete and other types of applications. Alrighty, folks, I got a boogie like a used tissue. I hope you're doing awesome and you have a great day. Go concrete.